Okay, so what we're going to be speaking of today is finding what we call volumes of solids of revolution. Okay, so the general idea is you want to think about, I have some sort of a region that's underneath a curve, okay, bounded between the curve and the x-axis. And I want to take that region and I want to revolve it around the x-axis. So I want you to think about how as I revolve this around the x-axis, notice what kinds of shapes are being created.
Okay, so let's take a look at this concept of revolving a region around the x-axis. Okay, so I want you to first think about this one line segment right here. What would happen if we rotated just this line segment around the x-axis? Okay, so let's take a look. If we revolve just that one line segment around the x-axis, you'll notice that what it creates is a disk. Okay, so what I want you to now think about, kind of think of if you've ever seen a CD stack, okay, like where you stack a bunch of DVDs or CDs. If you were to stack always does this to me. If you were to stack one CD on top of the next CD, on top of the next CD, on top of the next CD, eventually altogether what it's going to create is a volume of some solid figure. Okay, and again, what that volume is actually going to be representing is if I were to take this region and revolve this region around the x-axis, the volume of the figure that is created when I revolve that region around the x-axis is what's going to end up creating the volume of this solid figure. Okay, so now we have to figure out, how do we actually figure out the volume of this shape right here? And it goes back to each of those individual disks. Okay, so if you take a look at each disk, how do we find out the area of just that one disk? Well, think of the area of a circle. It's pi r squared. So obviously you're still going to have pi times something squared. You'll notice that the radius is not some sort of, constant thing. It's actually the function value between the x-axis and the actual function itself. So what we need to do here is we need to add up each of these individual disks. So how do we add things up in terms of calculus? That's what integration is for. So our formula is going to be pi r squared, or pi times f of x squared, and as I integrate from left all the way to the right of the region, what that's going to do is create that solid figure.
Okay, so let's write down that formula that we just saw by looking at that digital demonstration. So it's the integral from the beginning of the region to the end of the region. So sometimes that's given to you, sometimes you have to find intersection points. When you're only dealing with one curve, it's pi times f of x squared dx. Again, keep in mind this is based off of the area of a circle formula, pi r squared, but your radius is just the function value, and again it needs to be like f of x because it changes as you work your way through that figure. Okay, so if you take a look at the example we have, let's say figure 1, figure 2. Figure 2 is created by revolving the region, x squared minus 4x plus 5 on the interval from x equals 1 to x equals 4 and y equals 0 about the x-axis. Okay, so what's nice in this question, you don't have to find any intersections. You already know that the integral is going to go from 1 to 4. Okay, the pi can be written either inside the integral or outside, because remember that it's a constant, and your function values are coming from the function x squared minus 4x plus 5. That whole quantity is squared dx. Now this is definitely something that's doable if you had to do it by hand, but again, for today we're just kind of focusing more on like what's the concept of how you set up the integral, and then you can go right ahead and plug this in your calculator. Now as I mentioned with the area questions, I would definitely suggest that you consider your function as y1, like plug that in your graphing calculator, and then use that abbreviation y1 when you go to do your calculation. That way you don't have to worry about making mistakes with any parentheses when you go to do your calculation. As always, don't forget the AP standard is 3 decimal places, so 49.009 is going to be the value of that volume.
Okay, so now what we're going to do is look at what happens when you revolve a region bounded between two curves around the x-axis. It's still going to have that same idea of pi r squared, because you're still going to end up dealing with disks, but it's going to be a little different as we revolve, the distance between a region around the x-axis. So again, I want you to think about the fact that you're revolving around the x-axis. So just take a look. This is the idea of what's happening. As I revolve this region around the x-axis, once again, I'm going to create some sort of disk. Well, except this time you're going to notice it's almost more of like a washer. It's a disk that has almost like a hole in the middle. So if you think back to like area of the shaded region, back to when you were in algebra in the beginning, you would take the area of the entire large circle minus the area of the inside circle, and that would give you the area of that disk. So that's the idea of what we're going to be doing here. We need to find along this entire region, okay, as I go across this entire region, what is the area of each disk as I go from the beginning of the region to the end of the region, and as I add all of those disks together, that's going to create for me the volume of the figure that's created as I revolve around the x-axis. You can take a look. This is an idea of what this three-dimensional figure is going to look like. And again, similar to what we had done before, you're still adding up all of these disks together. So let's think about area of each individual disk is going to be pi r squared minus pi r squared, where you're going to start with the outer radius squared, and then you're going to end up with the inner radius squared. As I add up all those disks from the beginning of the region to the end of the region, think of them getting stacked on top of each other, they create this solid figure. Okay, so we're going to go back to the lesson and you're going to take a look at what the formula looks like for.
Okay, so let's write that formula down. If we want the volume of a solid revolution bounded between two curves, it's going to be the integral from a to b. Most likely those are the intersections between those functions unless the interval is specifically given to you. The general idea is pi r squared minus pi r squared, okay, where your big R is your outer radius and your little r is your inner radius, and many times, in these basic examples that will relate to the upper and the lower function. An alternative way that you can also see this written is to have the pi factored out. And if you choose to do that, that's absolutely fine, but just don't forget when you go to plug it in your calculator, don't forget about that pi because that's a common mistake. And then again, it would be the outer radius squared minus the inner radius squared, because again, it's still this idea of adding a bunch of disks together, except this time you have almost more what looks like washers or, donuts or whatever you want to think of it like that. And again, as you integrate, you're stacking all of them together. So let's take a look at an example. It says, let's suppose we're rotating an area bounded between the two curves, f of x equals x squared minus 2x plus 3, and g of x equals x plus 3. The first thing that you should do is go and graph what this would look like if you were actually trying to find the area. Go and graph this region in your calculator and honestly sketch a picture of what the region looks like. So if we sketch this, it's some sort of a parabola that looks sort of like this. And you have the line y equals x plus 3. So the region that you are bounding is the region between these two curves, okay? As you take a look at the intersections, those will be important because they become the bounds of your integral. You'll see these two functions intersect at 0 and at 3. Okay, now what I like to do when I'm trying to do these volumes of revolution, I like to sketch a region of what it sort of looks like so I can see what makes the outer function, what makes the inner function. So what I like to do is I take the region bounded between those two curves, just the region itself, and I draw it being reflected over the axis of rotation. Okay, so the axis of rotation here is the x-axis. I'm going to draw it reflected over the x-axis. Okay, imagine again you're making these little discs or circles as this revolves around the x-axis. And now you should be able to easily figure out what makes your outer radius, okay, and what makes your inner radius. So if you look at these two functions, I think it's pretty clear that the linear function is making the outside edge of our function. So the outer radius is that linear function x plus 3, or g of x, if that's what you'd like to do in terms of setting that up. Your inner radius then is left to be the other function, x squared minus 2x plus 3. And so therefore, if you were to set up this particular problem, and again, this was called g of x, this was called f of x, feel free to use the abbreviations. Also feel free to use like y1 and y2. Just make sure you're plugging them in the correct order. So your integral would look like something like this. Integral from 0 to 3, pi times your outer radius squared, which is g of x squared, minus pi times your inner radius squared, f of x squared dx. Again, you're also welcome to factor out the pi if you want, but I have found that sometimes people make mistakes with forgetting the pi. It's up to you. At the end of the day, you're going to end up plugging in, round to 3 decimal places. This comes out to be 101.788, and that's the volume of that figure. So let's try one more example, or 1 or 2 more examples, just so you can kind of get used to the process for this. So you'll notice this time there's no graph provided. So the first thing you're going to want to do is graph this for yourself. So I'm going to set this up. The function y equals square root of x minus 2 looks like a square root function that starts at being shifted over 2 units to the right. It's being stopped at x equals 4. And it says, take this figure, this region you see right here, bounded also by the x-axis. So you're going to see right here that that starts when x equals 2, as it's rotated about the x-axis. Okay, so this is the region that we are trying to revolve. So the first thing that I would suggest you do is, again, obviously sketch your region. You can see right here that it starts at 2 and it ends at 4. So our integral is going to go from 2 to 4. You're going to try to envision what this looks like if this was reflected over the axis of rotation. So again, you can see this idea of disks that are created and added from left to right. This one, there is no inner function. Technically, I guess the inner function would be the x-axis, but this one you're not going to have to do an outer radius squared minus inner radius squared. It's just going to be pi times your function, which is the square root of x minus 2 squared dx. I'm going to do this one by hand, just do a little bit of practice. There's not often times that you can do them by hand. This one comes out to be a little easier because of the fact that you have the square root of something squared. Just do a little practice with our integration rules. So I'm going to move the pi to the outside. This is integrated from 2 to 4. X minus 2, square root of x minus 2 squared is obviously just going to be x minus 2 dx. So as you integrate, this comes out to be pi in front. Then I'll have x squared over 2. Remember that when you integrate, you're increasing your power by 1, dividing by your new power. Negative 2 becomes 2x, and you're now evaluating this from 2 to 4. Now, if you remember, if you want to still do this by hand just to practice, but also use the calculator to assist you, you can think of calling this something like big F of x. So then you'd end up doing something like big F of 4 minus big F of 2. Obviously, again, don't forget to multiply it by pi. And then at the end of the day, this comes out to have a value of, hang on 1 second. Oh no, I lost it. This one comes out to be a value of either 2 pi, if you wanted to leave it as an exact value, or if you round it to 3 decimal places, 6.283. All right, so let's take a look at another example. This time you have no graph provided, you're not provided with an interval, so definitely the first thing you should do is go in your graphing calculator, as I did here right here on the right, and graph what your function looks like. Okay, so let's draw yourself a little sketch. You once again have some sort of a parabola and some sort of a linear function. Okay, and in particular what we really want to focus on is that region that's shaded between those two curves. So if I focus just on that region for a second, okay, this is the region that you want to be envisioning is being reflected over the x-axis. So draw yourself an image of what that looks like as it's reflected over the x-axis. That way you can get that idea of these little discs or washers that are being created. The other thing you need to get from the graph are what are the points of intersection. So if you look right here on the graph, you can see they intersect at negative 2, 1 and 2, 9. So that means that our integral is going to begin at negative 2 and end at 2. Okay, so let's go to this full picture here. This is what we are finding the volume of using these two functions. So as I start to set this up, this is going to be the integral that goes from negative 2 to 2. Okay, it's going to be pi times your outer radius squared minus pi times your inner radius squared. So let's think about what's our outer radius, what's our inner radius. Okay, hopefully you can see right here the outer radius is being formed by that linear function. So our outer radius is 2x plus 5, or g of x if you want to use the abbreviation. Okay, so we're going to do pi times g of x squared. And then our inner radius obviously is the other function. That would be f of x, or x squared plus 2x plus 1. So you're going to have pi times f of x squared dx. I very much highly recommend using that idea of using like y1 and y2, and be careful with the way you type them in. Like if you type this one in as y1 and type this one in as y2, make sure you're putting y2 here and y1 here so you don't make mistakes with your calculation. I probably should have mentioned this earlier, but you should never be getting a negative volume when you're revolving something around an axis. It should always be a positive. If you're getting a negative, you probably messed up your inner and outer function. So if you go ahead and you plug this in your calculator, again, you can round to 3 decimal places. This comes out to be 227.